Now this time what we want to do is factorise this expression over real numbers and find values for cos pi on 5 and 3 pi on 5 exactly from that. So when we look at z to the power of 5 plus 1, we know that we can get the fifth roots of minus 1. So we know they would be equally spaced around the unit circle because it's got a modulus of 1, and one of the roots would be at minus 1, and then they'll be equally spaced at 2 pi on 5 around that unit circle. So if we drew them up, we'd see minus 1 there, and then we'd have cis 3 pi on 5, and then pi on 5, minus pi on 5. So we can see our roots there, and then complex conjugates there. So there's our 5 roots of z to the power of 5 minus 1, or z to the power of 5 plus 1 is equal to 0. So that's the roots of that equation. We also know that we can have z to the power of 5 plus 1 factorised down to this. So we just get rid of that one so we can make sure we can see it. So we can see that we get that expression as our factorisation of z to the power of 5 plus 1. Now, given that situation, we know that we can write z to the power of 5 plus 1 as the product of the roots there. So the z plus 1, minus the cis pi on 5, cis 3 pi on 5, minus pi on 5, minus 3 pi on 5. Those 5 roots that we just saw, so z minus each of those roots, multiplied out would give us z to the power of 5 plus 1, because they're all roots of that expression. So if we start to equate those, we get z plus 1 to cancel, which means that the 4 other roots must be equal to this expression here. So that we can set that up. Z to the power of 4 minus z cubed plus z squared minus z plus 1 is equal to the multiplication of those 4 expressions. Now, we can't do much with this one, so let's play with this one and expand it out. So we just expanding the cis form. So because it's minus cis of pi on 5, we get minus cos pi on 5 minus I sine pi on 5, and we go along similarly there. Now what we want to do is start to simplify this expression. So we'll multiply these two. Now remember when we multiplied two expressions where we've got the roots being complex conjugates, what we get is the z squared minus 2 lots of the real part times z. So the real part would be cos of pi on 5, because those parts would cancel out. And then plus the multiplication of the two complex conjugates gives us the 1. So we know we can get that expression. So if we remember that simple way to do that, then that makes life easy. If not, just expand it out, like multiply each term by the other terms and collect the like terms and cancel, and we'll get that one. Similarly, the 3 pi on 5 and the cis minus 3 pi on 5 are complex conjugates, so we do the same thing. So we get z squared minus 2 times the real part times z plus the multiplication of the conjugates, which gives us 1. Now, if we expand that out, that gives us this expression, z to the power of 4, 2 lots of cos pi on 5, 3 pi on 5 with the z cubed, and we multiply it, and then 2 lots of that expression times z squared, and so on. So that's just the expansion of those two. Now remember, these two are equal, so we can start to equate the coefficients. We equate z cubed, we get that expression, and z squared, we start to get get expressions that we need to use. So z cubed would give us that one equal to minus 1, and then so we can divide by minus 2, and cos pi on 5, cos 3 pi on 5 is equal to half. And then if we get z squared, then we get this situation. So we can manipulate that down to the multiplication of those two gives us a quarter. So we've got two values there, multiplying to give us minus a quarter and adding to give us a half. Well, we could say that these two could be roots of a quadratic equation, because the sum to give us a half, multiply to give us a quarter. So we can get a quadratic equation that looks like that. So we can manipulate our quadratic equation to give us that expression, which if we apply the quadratic formula, we're able to bring it down to 1 plus or minus root 5 on 4, which means we get two values, 1 plus root 5 and 1 minus root 5 on 4. So we know that cos of pi on 5 would be 1 plus root 5 on 4, because that's going to be positive. And 3 pi on 5 is in the second quadrant, so that's going to be the negative one. So there's our two values of cos pi on 5 and cos 3 pi on 5 from our manipulation of that expression and creating a quadratic equation there. So in question 5, we're given this situation. Don't need to prove that. By solving cos of 6 pi theta on x equal to 0, show that we can get these two results. Okay, so we know if we got cos 6 theta is equal to 0, then that gives us a general equation of 6 theta equal to pi on 2 plus k pi, which we can divide by 6 and get this situation, 2k theta be equal to 2k pi plus 1 over 12 times pi. Now putting in values of 0 to 5 gives us those values. So there's those 6 roots. There's those 6 values where we put those in and multiply it by 6, it would give us a value of 0 when we take cos of it. So if we look at the other side of the equation, 32 cos 6, that theta to the power of 6, and 48 cos theta to the power of 4, and so on. If we let x be equal to cos squared for that situation. So basically we're going to come down to this. 32x cubed minus 48x squared plus 18x minus 1. So the roots of that one then would be this situation, cos squared of 2k plus 1 pi on 12. Because we're going from there, and because it's cos squared theta, well, that's cos of theta, then taking cos of theta and then squaring it. So the values then would be able to say, well, the product of the roots then, if they're the roots we've got, then we're able to take k is equal to 0, 1, 2. So there we're going to get 3 roots of that cubic there. Multiply that out. So when it's 0, when it's 1, when it's 2, gives us 1 on the 32. So minus of minus 1 on 32. So realizing that part's going to be equal to a half, because cos of 3 pi on 12 is cos of pi on 4, which is 1 on root 2. So we're able to get that being a half. That means the multiplying by 2 on both sides gives us the 1 on 16. So that gets rid of the half. And so cos squared of pi on 12, cos squared of pi on 12, take the square root of both sides, gives us a quarter. So there's that first expression. So from the product of the roots. So seeing we've got a sum there, you might think, well, let's go to the sum of the roots for the other one, and we can do that. So cos of pi on 12 all squared, 3 pi on 12 all squared, 5 pi on 12 all squared, they're the 3 roots there. Again, we know that was going to give us to a half because of that situation. And that's equal to the 48 on 32 from the cubic we just created, which comes down to 3 on 2. Now, we've got those two then, plus the half is equal to 3 on 2. Subtract half on each side. Well, that 3 on 2 minus half gives us the 1. So there's our expression for the sum of the roots there when they've both been squared. So that's how we do that one. That's again not easy. We have to live and learn how we can start to manipulate a lot of these equations. So we want to see as many expressions as possible. So here's some in these questions here. So have a look. If you're not sure, again, look at the manipulations, see how we can manipulate it and get our results of those equations and solve them there.